Welcome to the Explainer. Today, we're going to tackle a huge topic, maybe the most important algorithm in all of modern AI, backpropagation. It's the secret sauce, the magic trick that lets machines learn from their mistakes. And we're going to break it all down piece by piece. But, really think about that for a second. We say a computer learns to recognize a face or translate a language, but how? What's actually happening inside that bundle of code and circuits that allows it to get better just by looking at examples? Well, the answer, believe it or not, comes from a really elegant idea in calculus. And before you run for the hills, don't worry, we're not going to drown in equations. We're actually going to explain the whole thing with a cake. So let's get to the heart of the problem. A neural network is basically a prediction machine. And when it gets a prediction wrong, that creates an error. The whole point of learning is to make that error smaller. To do that, the network has to figure out which of its millions of little internal knobs, or weights, it needs to adjust, and, crucially, by how much. And this, right here, is the key. For every single one of those little knobs, we need to ask a simple question. How sensitive is the final error to you? In other words, if I wiggle this one specific weight just a tiny bit, does the final error jump up or does it drop down? This measurement of sensitivity is what mathematicians call a derivative, and it's the perfect way to assign blame for a mistake. Okay, to make this whole sensitivity thing super intuitive, let's forget about networks for a minute and talk about something much tastier, baking a cake. This is going to help us understand the mathematical engine behind backpropagation, a little thing called the chain rule. So, just imagine the final taste of your cake depends on how much sugar is in it. Makes sense. And the amount of sugar, well, that depends on how many scoops of sugar you add. See, it's just a simple chain of cause and effect. Change the number of scoops, and that's going to have a direct, knock-on effect all the way down to the final taste. And here's the beautiful part. If you want to figure out the total impact your scoops have on the final taste, you just multiply the individual effects together. How much does one scoop change the sugar amount? And how much does that amount of sugar change the taste? Multiply those two sensitivities, and you've got your answer. That simple multiplication, that's the entire chain rule. Seriously. All right, time to head back from the kitchen to the computer. We're going to take that exact same logic from our cake, the idea of multiplying sensitivities, and use it to trace an error backward through a simple network. Whoa, okay. I know, that looks intimidating. It's the kind of thing that makes you want to close the video. But I promise, just stick with me. This is just our cake analogy written down with fancy symbols. All it's saying is, to find the effect of that first weight way at the beginning on the final error way at the end, you just multiply all the little sensitivity steps in between. Let's decode it. See? Every symbol just stands for something simple. E is just the error, how wrong we were. W is one of those knobs we can tune. A is what a neuron spits out. And that funky little delta symbol, it just means the sensitivity of. So delta E over W just reads as the sensitivity of the error to the weight. That's it. It's our blame calculator. So, to see how this all works, let's use a super simple network, just two weights. We're going to give it an input of 0.5, and our goal is to teach it to output 1.0. We'll just start with some random guesses for our two weights, W1 and W2. We push our input through the network, and it makes its first guess, 0.601. Not too shabby for a first try, but the right answer is 1.0. So, we have a small error. And now, the learning begins. The network has to figure out how to adjust its knobs to get closer to the right answer. And here comes the magic. We're going to work our way backward from that final error using our chain rule to figure out exactly how much that second weight, W2, was to blame for the mistake. We're building our chain of sensitivity, link by link. We do it in 3 easy steps. First, link 1. How sensitive is the error to the final output? We calculate that. Second, link 2. How sensitive is that output to the signal it got right before it? Got it? And finally, link 3. How sensitive was that signal to the weight W2 itself? And there's our last link. And now for the big reveal. We just multiply those 3 sensitivities together, and we get 0.057. That's it. That one number is the blame. It's the total sensitivity of the error with respect to that second weight. We now know exactly how much that knob contributed to the mistake. Now here's where things get really clever. What about the first weight? Do we have to start all over again? Nope. And this is the trick that actually gives backpropagation its name. Instead of recalculating everything, we just take the chain of blame we've already figured out and extend it one step further back. We are literally reusing our previous work and propagating the error information backward through the network. It's incredibly efficient. So now that we've seen it in action with a simple example, let's see how this exact same pattern gets turned into general rules that can power any neural network, no matter how ridiculously massive it is. So this first formula is just a tidy way of calculating an error signal for any neuron in the network. It might look a little dense, but it's just saying what we already did. A neuron's share of the blame is just the sum of the blame signals coming from the layer in front of it, adjusted for how strong the connections are, and then multiplied by its own local sensitivity. We're just passing the blame backward. And the best part is, all that work leads to this beautifully simple rule for actually updating the weights. The amount you need to change any given weight is basically just that error signal we just calculated times the signal that flowed through the weight in the first place. This simple math tells us exactly how to nudge every single knob in the right direction. Okay, so we've done the math, we've baked the cake. Let's zoom out now and just appreciate for a second why this whole process is so incredibly powerful. This is the real magic. We never have to tell the network what to look for. If a network misclassifies an angry face as a happy one, backpropagation just automatically traces that error backward. It figures out, on its own, that the neurons looking for a smile were too active and the ones for a furrowed brow weren't active enough, so it nudges them. And after doing this thousands and thousands of times, the neurons just organize themselves. They become useful detectors for things like eyes, noses, smiles, all by themselves. And that kind of leaves us with a pretty big question, doesn't it? Backpropagation is, at its core, a simple, elegant algorithm for learning by tracing your own mistakes. So you have to wonder, what's the ultimate limit for a system like that? How far can it go?